Yeah, so the title is Infinite Volume and Infinite Injectivity Radius. So that's joined with the Mikolaj, Tsachik. And okay, let me start by the main theorem, or one of the main theorem that we proved is the following theorem. So let G be a simple Lie group of real rank at least 2, and lambda inside G a discrete subgroup of infinite covolume. A discrete subgroup. So let M be G mod K is a symmetric space. G mod K mod lambda is the corresponding locally symmetric orbifold. Then if the volume of M is infinite, then M contains or for every M contains ball of arbitrarily large radius. So for every R, there is P inside M such that the injectivity radius is at least R. So this was a conjecture by Margulis, so that this result is in a sense unique, in a sense that it applies to arbitrary discrete subgroup of G, where there are plenty of results, and there is a beautiful theory for lattices, and this result does not assume, or it's even more interesting when gamma is not a lattice. But it also can be read as a result about lattices. It says that if the injectivity radius of M is bounded, then M has finite volume. So in a sense, maybe you can use it, or it can be useful to show that certain groups are lattices. For instance, Margulis has a wonderful proof of the Borel-Arishandra theorem. He showed that every arithmetic group has finite volume by showing that the injectivity radius goes to 0 when you go to infinity. So if you apply this theorem, you need a bit less. You just need to show that the injectivity radius is bounded and does not go to infinity, and it will imply finite volume, but only in higher rank. So this theorem is not true in rank 1. So let me give an example. So suppose that the rank of G is 1, like the hyperbolic space, or the complex hyperbolic, or the quaternionic hyperbolic, and let gamma inside G be a co-compact lattice, a uniform lattice. Let lambda inside gamma be normal, non-trivial of infinite index. So gamma is a hyperbolic group, so every hyperbolic group admits plenty of normal subgroups. So in particular, the normal subgroup theorem of Margulis does not apply in rank 1. So there are such lambda. Then the manifold M, which is G mod K mod lambda, has bounded injectivity radius. Although it is of infinite volume. Ariel, if you can mute the rest, it will be helpful. And the proof is as follows. So consider let alpha be inside lambda, non-trivial. Let omega in G be compact fundamental domain for gamma. and let D be the maximum of the displacement gamma XX, where X belongs to omega. So, okay, I think of it in the symmetric space. So then the injectivity radius inside M of any point is at most D. And to see that, consider let P tilde be inside G mod K a lift of P, and take gamma such that gamma inverse P tilde, you can bring it into the fundamental domain. And then think of the element gamma alpha gamma inverse, or here it was alpha. The max, this is, since the fundamental domain is compact, alpha is some bounded displacement on the fundamental domain. And now I consider this element. This element is inside the normal subgroup lambda, but the displacement of this element gamma alpha gamma inverse of P is the same as the displacement of alpha of the point gamma inverse P, which is inside omega, which is bounded by D. So you see, in particular, when the theorem that holds, you cannot have it. The theorem implies the normal subgroup theorem. That's what. So when the normal subgroup theorem is not true, the theorem is not true. And the theorem has other application. For instance, it also, if you know the seven summarized result, that if you have a sequence of manifold with volume goes to infinity, then the injectivity radius goes to infinity. And this also can be deduced from that theorem. So in a sense, it generalizes both the normal subgroup theorem and the seven summarized result.
Tsachik?
Yes.
But can you prove the normal subgroup theorem for a non-uniform lattice as well?
Yeah. So you will see there is a probabilistic version of that. So let me define this property. So lambda inside G discrete will be called uniformly slim if the injectivity radius in G mod K mod lambda is bounded. And this is equivalent to say, and this is equivalent to say that there is C inside G compact such that lambda, any conjugation of lambda intersects C non-trivially. So that's uniformly slim. And then a remark, the lambda is not uniformly slim if you can conjugate it to intersect trivially every compact group. So if and only if the conjugacy class of gamma of lambda contains, in the Chabadi topology, contains a trivial group. If you can conjugate it, it can converge to by conjugates to the trivial group. That's a non-uniformly slim group. By the way, I use lambda to denote a group which are not lattices and gamma to denote group which are lattices. lambda could be a lattice, but a priori it's not. So let me state the theorem in a slightly more general case. So let G be now semisimple, center free, semisimple, and so connected, and suppose that the rank of each factor is at least 2. Lambda inside G discrete, then lambda is uniformly slim if and only if there is H inside G non-trivial, which is a semi-simple factor. It's a normal subgroup, so it means that it's a product of some of the factors such that H intersect lambda is a lattice in H. So that's the theorem in that case. And we also have variants of this theorem when you allow rank 1 groups. So, but before that, somehow the main idea was to consider random walks. So you know that a few years ago, people started to consider invariant random subgroups to get, for me, it was exciting to get new results about lattices, the deterministic group, by considering random subgroup, invariant random subgroup. But invariant random subgroup are limited and cannot be applied to general groups, while stationary random subgroups, so measures which are not invariant but stationary, are much more general and applies to much more general context. So, so the idea of considering a random walk is a good idea here. So, so let like in Uri talk, let me start with a probability measure on G. I will denote it by nu. It's a probability measure on G, which is a specific probability measure. So K is the maximal compact, and I take the convolution with a Dirac measure. So NK is Har on the compact, maximal compact, normalized Har, and S is some semi-simple element which acts by sufficiently good expansion on the unipotent radical of a fixed minimal parabolic. So for SLN, it will be an element, a diagonal element like that, such that AI is much bigger than AI plus 1.
But Tsachik, just so you know, it's like calling, reverting the role of epsilon and delta, this thing that you're doing.
What do you mean?
I mean, calling this nu and the other one mu is...
Yeah, I agree, but I got used to that. So, okay, after the talk, I can try to get used to the other, but let me do that. I'm think I'm more dyslexic than most of you. So I will use nu for the measure on G. So nu is the measure on G, and it's this specific measure, I'm not going to change it anymore. So it's a specific measure.
Tsachik, can I ask a quick question about the theorem?
Sure.
Lambda intersection H, does it need to be, can it be any lattice or does it need to be uniform?
Any lattice. Yeah, any lattice is uniformly slim. Any lattice is uniformly slim because the injectivity
it needs just to be bounded. Okay.
Yes. Think about the thick-thin decomposition. So the thin part is thin anyhow, and the thick part is compact. So any lattice is uniformly slim. And in higher rank, so in higher rank simple group, uniformly slim is equivalent to be a lattice. But for higher rank simple group, for product of simple group of higher rank, uniformly slim is equivalent to contains a lattice in subproduct. So now let sub G be the space, the Chabati space of a closed subgroup of G. So this is a compact metrizable space. It's a nice space on which G acts by conjugation. And inside, let sub discrete G be the subspace, the open subset of a discrete subgroup. And the idea is to apply a random walk on that space. So G acts by conjugation. So consider mu n, which will be the Cesaro average when I goes from 0 to n minus 1 of nu to the I convolution with Dirac on this lambda. I start with the discrete group lambda, and then I start to conjugating by a random element from U, and I iterate it and take the Cesaro average. Then since the space of measures is weak star compact, there will be a limit to the sequence, and this will be a stationary measure. And let mu infinity be a stationary limit. So it's a stationary measure, which is a limit of this sequence. So any limit of the sequence will be stationary. So so here is the theorem that we proved, and now it's one of the theorems. So let G be the product, G1 cross G2 cross GM, be center free, semisimple, without compact factor. So now I allow rank 1 factors, but suppose that lambda in G does not intersect a non-trivial semi-simple factor, which means a non-trivial subproduct of the GI by a lattice. I cannot only assume that it's not uniformly slim, because I allow rank 1 factors, and in rank 1, you can be uniformly slim without being a lattice. Then the stationary limit, then mu infinity is supported on discrete subgroups of the product of rank 1 a simple factor. So there is some rigidity phenomena here. So you start with the groups with rank 1 factor and higher rank factors, and then you do this random walk, and the random walk escapes from all the high rank factors and limits into the rank 1 factors. In particular, if all these factors are of rank 2 or more, then there is a unique stationary limit, which is the Dirac measure on the trivial group. And in fact, if you look in the paper, there are some variant with more information. For instance, if you assume that G has property T, so all the rank 1 factor are of the form SPN1 or F4 minus 20, then you can say more about the product, the limit. The limit will not just be a discrete subgroup of the product, but will be a product of discrete subgroup in the factors. And in each factor, the limit will be either trivial or Zariski dense, and if the group that is started is uniformly slim, then the limit will also be a product of uniformly slim groups. And this result eliminates some cases, because if you start with a group which does not contain large product, then also in the limit you cannot have large products. If you have large commuting subgroup in the limit, you must have large commuting subgroup in the original group. So sometimes you can say more, but for that you have to assume additional assumption, which are property T.
Tsachik, do you think T is necessary for this?
What?
Or just an artifact of the proof?
Sorry?
For product of rank 1 groups, do you think T is necessary for the separation into factors?
I don't understand the question.
I said that this other thing that you proved for rank 1 groups, you do under the assumption of property T.
Yeah.
Do you think
don't assume property T? If you don't assume property T?
Yes.
Okay. There are some things that are necessary and something that we don't know, but we are limited because of the Zimmer result. Yeah. So it's something in between. So we have example of in product of rank 1, we have example of interesting. For this theorem, you cannot really improve it by much. Even if you prove the Zimmer for product of rank 1 without property T, but there are other statements that you can improve. Yeah. So let me just before the break state two results. One is if you want Neveu-Zimmer type theorem. So it's Neveu-Zimmer applied to this specific situation that so stationary measure on the space of discrete subgroup. So let G be as above, and let mu be a stationary measure on the space of discrete subgroup of G. So it's a stationary measure on the compact space of a subgroup of G, of closed subgroup, which give measure 1 to the open subset of discrete subgroup. Suppose that almost surely the intersection with every rank 1 factor is trivial, and this is a necessary assumption. Then mu is invariant, is an IRS. So it's an IRS, and this yeah. So this is the Neveu-Zimmer type result for this specific. You can state actually the same result with a weaker assumption. You don't need to assume that the intersection with each rank 1 factor is trivial. It's enough to assume that it's not Zariski dense, and that's you get the same result. And now,
what do you mean by intersection? Intersection of what with the rank 1 factors?
So you have a measure on the space of subgroup. So a random object there is a subgroup. So almost surely this subgroup intersect trivially every rank 1 factor. That's the assumption. And the second result, and then we go to a break, is Zimmer type result, and it follows from Zimmer with in this situation. So let G be as above, and assume G has Kazhdan property T. then let mu be as above. Then mu is mu gamma for some gamma inside H inside G, where H is a normal subgroup and gamma is a lattice. And what do I mean by mu gamma? H mod gamma is a probability measure, and you have a map from H mod gamma to sub H, which is inside sub G, sending an element H gamma to the conjugate H gamma H inverse, and you push the probability measure from H mod gamma to here, and you get, and this will be mu. And so this is the Neveu-Zimmer type result. So this is basically somehow most of the main result that we proved. And maybe now it's a good time for a break or for questions about the results. So let me just answer a bit quickly to Yair's question. Yair, I gave example that a normal subgroup in a co-compact lattice are uniformly slim. And Yair asked me if a normal subgroup in a non-co-compact subgroup are also uniformly slim. So in fact, this I don't know. But what I can tell you but our theorem implies also the normal subgroup theorem in that case, because our theorem says that if you do a random walk on the manifold, then with probability tending to 1, you will spend most of the time in the R thick part for every R. You combine it with the Eskin-Margulis theorem, which is about random walk on G mod gamma, and they tell you that with some positive probability, you spend time in the thick part of a lattice. So if you do it for a lattice and a normal subgroup in the same time, then you see that in the lattice you will be in the thick part, and in the normal subgroup you will be in the very thick part. So that's somehow contradict each other. So okay, I will not say more details here because it will confuse me. But we can talk about it later. Yeah. So now it's a good time for a break. If so, let's do break until 25 to 4.
Excellent.
So maybe pause the recording. So we continue, and now it's the part of the proofs.
You're unshared again.
I'm unshared. So just a moment.
Okay.
So,
excuse me. So before you continue,
yeah,
I have a question about the implications between the theorems that you stated. I lost track of things. Can you briefly repeat?
Did I say implications? Okay.
So the last two theorems, they imply the red one that you stated, or how does it go?
What was the red one? There was
the bottom. In the bottom, in the end, you stated 3 theorems.
No. The last two theorems do not directly imply the theorem, the red theorem.
Okay.
So there is a decomposition theorem that we proved that implies all 3 theorems here, but I didn't state it here.
Okay.
I didn't state it.
Okay.
Yeah.
Thank you.
So yeah, thank you. It's a good question. So okay, so let Lie G be the Lie algebra. So in particular, from now, assume that G is simple. and the rank now of G is at least 2. So our paper is 22 pages because we do a lot of work to deal with the general semisimple case, and in particular, the case where there are rank 1 factor. But when G is simple of rank 2 or more, then you can see the idea in short, and many of the technicality become redundant. So, okay, consider the Lie algebra, and let fix a norm, be a norm on the Lie algebra. Such that the exponent from the unit ball to, let's say, U inside G is a diffeomorphism. One-to-one diffeomorphism, where B is the set, the unit ball. And then I define for gamma inside G, I define I of gamma to be the discreteness radius, and I of gamma, lambda, I of lambda will be, let's say, the minimum between 1, so it's at most 1, and the norm of log of gamma, where gamma is inside lambda minus the identity. And if you want, and the log is well defined, so lambda is in this neighborhood. So if my group intersect trivially this ball, then I take the injectivity, the discreteness radius to be 1, and otherwise it will be the norm of the smallest non-trivial element. And and then here is a theorem that from a paper with Ariel Levitt and Margulis. And the theorem says the following: there exists a constant delta and a constant C and a constant beta, B, such that for every lambda inside G discrete, the integral of I of lambda to the minus delta d nu, and nu is the measure that I introduced before, the convolution with the bi-k invariant measure with the semi-simple expanding element. This is C times the value before the integration plus B. So if I denote by U of lambda this I of lambda into the minus delta, then basically it says that nu convolution U at any point lambda is at most C times U of lambda plus B. And let's take this for granted. Yes?
The integral is d nu.
I forgot to write. So yeah, the integral is d nu of G. I conjugate by G. Yeah. G acts on the space of subgroup. Yeah. But basically, this is what you should remember. Convolution of nu with this function satisfy this inequality. Sometimes functions that satisfy such inequality are called Margulis functions. So from this, we can deduce the following theorem. which is the starting point of our work. So let mu be any measure on the space of discrete subgroup, and mu n as above will be the Cesaro sum of nu to the I convolution mu. I go from 0 to n minus 1, and this converge to a stationary limit or a subsequent. Yeah, you can take some stationary limit. I will write it in short like that. Then the stationary limit is also supported on the space of discrete subgroup. So a stationary limit is almost surely discrete. That's the theorem. And let's see the proof, because it's can be written very shortly. Proof. So how do you show that a measure on subgroup is supported on discrete subgroup? It's enough to show, we need to show that for every epsilon, there is V inside G, identity neighborhood, open, such that the probability that subgroup intersect V non-trivially, is smaller than epsilon. This will tell you that if for every epsilon you can find such an open set, then the measure is supported on discrete group. So it's enough to show that there exists such V such that nu to the I convolution mu has this property. Because mu n is the average of such measure, and each of them satisfy this, then also the average and also the limit. So I will tell you what to take. So
to show that there exists I such that for every bigger I.
Yeah, but I will show you that for every I. So I'm cheating a bit, but you will see immediately. So consider the integral of u of lambda d nu convolution mu. This is smaller than c times u of lambda. Yes, like this. U of lambda g d mu plus b. And if you iterate this I times, then you see that the integral of u of lambda d nu to the I convolution mu, I times will be less than c to the I, this integral, plus b minus something like that. So suppose this is finite. A priori, it does not have to be finite, but this is where I'm slightly teaching. But if this is finite, then this is bounded by some constant. What is the constant is this integral plus this constant, because c is smaller than 1. And the fact that it's not finite is not important. Like you can, yeah, believe me, it's not important. Anyhow, so or if you want, state the same theorem when you start with mu, which such as this integral is finite. Then it's then this is a proof. And then I tell you, what do you take? You take v to be the set of all, what is V? V will be, where did I write it?
That's time. I mean, before you proceed, can I say something about this proof?
Yeah, but let me just write what is V. V will be the set where the log V will be the set of all G in G, such that the log of G, the norm of that, is smaller than epsilon over m to the power 1 minus 1 over delta. Yes, and this is, yeah, this will work. Okay. What, Uri?
Sorry for interrupting, but I mean, I just wanted to give some perspective about this trick of using this Margulis function. So Margulis design, or maybe this is a variation of tool that existed even before.
Yes.
A way to show that mass does not escape to infinity when you apply convolution, and this is when a certain function satisfies this A f plus b property.
Yes.
And
this idea of we apply it here, but this idea appeared before, in particular in Eskin Margulis' work, when they studied random walk on G mod gamma. Yeah.
Right. Classically, people use it to show that random walks on G mod gamma do not escape to the cusp. But here, this is very nice. I mean, they use it, Tsachik, Aryeh, and Margulis, probably to show that something does not escape to infinity, where infinity is the non-discrete subgroups inside subg.
Yeah, so this theorem is by me, Collage, Tsachik, and me. With Margulis and Aryeh, we prove this thing very effectively with specific constant that we write explicitly, because we want to get some very explicit estimates on several statements like Kazhdan Margulis theorem for Lie groups. But here, for the work with the Collage, we don't really care what are the constants, just that they exist. And then we apply this ideas of Eskin and Margulis, and we get this. And then let me recall Neveu-Zimmer theorem for this that Uri explained to us very beautifully in the previous talk. Neveu-Zimmer theorem say the following. So if x mu is a stationary G space, then either mu is invariant, or there is a parabolic factor, a measure preserving factor map from x mu to G mod Q, the stationary measure here, for some parabolic Q. So this is the Neveu-Zimmer theorem. So now I can complete the proof of our theorem. So we wish to show that if the volume of G mod lambda is infinity, then the stationary limit of this random walk is the Dirac measure on the identity. So, okay, let Q be a parabolic subgroup. So, subgroup. And let Ln be a Lévy decomposition of Q. So N is the unipotent radical, and L is the reductive subgroup. So N is well defined and L is not well defined. And let A be the center of L. So I do some very elementary facts about parabolic group. So here is a lemma. An A invariant probability measure on the space of discrete subgroup of Q is trivial. No, is supported on subgroups of the Levy. That's the first. That's the first lemma, and why is that? Proof. There exists A in the center, which acts by expansion on N, on the unipotent radical. You can find such a thing, and therefore, if you have with non-trivial probability, you intersect N, or you don't intersect L, then you can push this stuff to infinity. So this is, if you want, the intuition for this lemma. The proof itself is not 1 line, but maybe 7 lines in the paper. So there's no such a measure must be contained in L. The next lemma is that the intersection of all the conjugation of L over the unipotent radical is trivial. Okay, this is actually central, but let's assume that G is center free, so this intersection is trivial. And so, as I said, the N is canonic, so it's a radical, it's a normal, it's well defined, but L in the Levy decomposition is not canonic, as always, and if you do the intersection of all the choice of L, then it's trivial. So a corollary of these two lemmas combined together is the following. So let P inside Q be minimal parabolic. Then a P invariant probability measure on the space of discrete subgroup of Q is trivial. It must be the Dirac on the trivial group. That's the only P invariant such measure. That's a consequence. Why? Because N is contained in P. The unipotent radical of L is contained in P. So now we can apply the stuff that Uri told us in the last lecture. So let's now complete the proof of the theorem. So as you see, in the simple case, it's really straightforward. So okay, so G is simple, and rank of G is at least 2. So then if mu infinity is invariant, then the Stuck-Zimmer theorem tells us implies that either mu infinity is the Dirac on the trivial, which is what we want. So this is fine. Or mu infinity is mu gamma for gamma a lattice. For gamma a lattice. Now, a lattice in a higher rank simple Lie group is locally rigid. So by the way, mu infinity is always supported on the conjugacy class of lambda. If we start with lambda and you do this random walk, so you always stay in the conjugacy class of lambda, and in the limit you will be in the closure of the conjugacy class of lambda. So, so that implies that gamma is contained, the lattice gamma is contained in the conjugacy class of gamma. In the closure. So you can approximate lambda, a gamma by conjugate of gamma. But gamma is locally rigid. Gamma is locally rigid implies that actually if lambda to the g is too close, is sufficiently close, close to gamma, then then it is then it contains a conjugate of gamma. So, but if you contain a conjugate of a lattice, this implies that lambda is a lattice. A discrete group that contains a lattice is a lattice, and this is a contradiction because we assume that lambda is not a lattice. Okay, that's deal with the case that mu infinity is invariant when we apply Stokes-Zimmer. Oh, by the way, I didn't say, maybe I jumped, but this fact that stationary limits of measures supported on discrete group is still supported on discrete group is what allow us to do this random walk, starting by a specific lambda and start to conjugate it, and then to say that the limit is also of this type. The limit is supported on discrete group. So,
Tsachik, why did you assume that lambda is not a lattice? I mean,
no, if lambda is a lattice, then it's uniformly same. And then I consider lambda, which is not a lattice, and I want to show that the random walk converge to the Dirac mass on the trivial group.
Okay.
And so I take this random walk, I take a stationary limit, and I say if the stationary limit is invariant, then fine, because of Stokes-Zimmer. Because of the theorem before, it's supported on discrete group, and because of Stokes-Zimmer, if it's invariant, then it's an IRS supported on discrete group, so it's other trivial. Actually, to apply Stokes-Zimmer, maybe you don't even need that it's supported on discrete group. In that case, it follows from Stokes-Zimmer. Suppose now, if you want, by in contrary, suppose by way of contradiction, that mu infinity is not invariant. So if it's invariant, then we're done. And now we show that if you assume that it's not invariant, we actually get that it is invariant because it must be the trivial, the Dirac on the trivial. So by Neveu-Zimmer, we have a parabolic factor. A measure preserving factor, if you want, sub G mu infinity, and it factors to G mod Q nu Q. and and then by universality of the Poisson boundary, that we explained us, which is G mod P, we get a map from G mod P. There is a unique map. We have a unique map from G mod P to sub G, and similarly a map from G mod P to G mod Q. Sorry, not to sub G, to probability measure on sub G. And to probability measure on G mod Q, such that this diagram commute, because this is so Uri explained that very nicely. The way I like to think about it. Okay, I'm less used to this stuff than Uri, but so if you want, we usually think of the Poisson boundary of a group as the space that L infinity of the Poisson boundary is correspond to the harmonic function on G. So if you want to say that a measure in this space is new stationary, it just means that the map, its orbit map from G goes to G times mu is harmonic. The orbit map is harmonic, so the measure must be, if you want, a barycenter of a map to the space of measure. Okay, maybe this wasn't such. I shouldn't try to say it in my words after Uri explained it in a much better way. But anyhow, we get such a map. Now this map, we know what it is. So every this map GP goes to the Dirac of the conjugate of Q by G. So so that's the unique P invariant measure on G mod Q is the Dirac on Q, and the unique GP, the unique GP invariant measure on G mod Q is the Dirac measure on this conjugate. So it means that if we look at the measure corresponding to a point here, and then we look at it here, it will be this measure. But that means that the stabilizer are contained in the stabilizer here, which is exactly this. So in particular, if you take a generic point with respect to the measure, suppose the generic point is P itself, we get a measure on subgroup of Q, which is P invariant. So we get a discrete measure. So if we denote this map by N of GP is a GP G inverse invariant measure on discrete subgroup of GQ G inverse. And the lemmas that we had before, or the corollary, says that there is no such measure. So the corollary implies that this is just the Dirac on the identity. And and therefore mu itself is the Dirac on the identity. So this is the complete proof, if you want, in the case that G is simple. Modulo details that you can look in the paper. Most of the paper is dedicated to the case where G is not simple. And in particular, where G has rank 1 factor, then things become much more complicated. And in particular, there are many open questions that remains about what are uniformly slim subgroup, for instance, in rank 1 factors, in rank 1 groups, simple groups. So does every uniformly slim subgroup contain the normal subgroup of a lattice, for instance? Or there are also questions about stationary limits of general discrete group inside rank 1 groups. We have some example, but we don't understand the full picture. But and again, there is something that I didn't say because I didn't go too focused about the precise best result that we can get. But if you try to get the best result, then you're also limited because of you want to apply Zimmer. And Zimmer is known where G admits property T, even in the case that there are rank 1 factor. If G admits property T, and you assume that every factor acts ergodically, then there is the Zimmer. And also, if you assume that only one factor has property T, then a result of Yair Hartman and Omer Tammuz says that you can apply Zimmer. But in the case that, for instance, for SL2R times SL2R and things like that, we don't know. So then that's one of the big open problems that are left in the theory of invariant random subgroup. And since we don't know the case there, so we cannot say, for instance, what are the uniformly slim subgroup of SL2R times SL2R? Do you have a uniformly slim subgroup that project densely to each factor and it's not a lattice? So the normal subgroup theorem is true for lattices in SL2R times SL2R. That's Margulis did it in all cases, including that case, but he gave a more difficult proof for that case. There is the beautiful work of Bader and Shalom that deals with the normal subgroup theorem in general locally compact groups, product of locally compact groups. But here it's something which it's a more general version than a normal subgroup theorem. So you are not inside a lattice, or even if you are inside a lattice, but not a normal subgroup of a lattice, then okay, maybe yeah. Even then, but if you also if you assume that there is no lattice in the picture, what can you say about something that sits generic in a product of SL2? At the moment, not much. So there are some left open problems. In the last couple of minutes, I would like to say that I also learned when working on this that when you think of invariant random subgroup, it limits you. You cannot say something general because, and for instance, in rank 1, sometimes when you start this random walk with a group, the stationary limit will not be invariant. So the stationary limit may be stationary but not invariant. So if you want to if you restrict yourself to deal with invariant random subgroup, which I find as a great generalization of lattices, considering invariant random subgroup, but to consider stationary random subgroup, it's even greater. So it even allows you to say things that you cannot say by just applying theory of IRSs. Okay, so I think I will leave now time for questions. If you have.
Tsachik,
Ken, yes.
can you explain again the role of Nebo-Zimmer? So before that, you had that all stationary measures on, so the corollary from further up, I think.
Yes. So here when the measure is invariant, I apply the Zimmer. I say that by Stokes-Zimmer, either I'm here or I'm mu gamma for a lattice. And by local rigidity, I cannot be mu gamma without containing gamma originally.
I meant a bit further. I think it was in black. Here. So the corollary is.
Oh, for this, this is before Neveu-Zimmer. This is the abstract results about parabolic subgroup. So I say that if you consider discrete subgroup of a parabolic group, actually for this thing, Uri showed me maybe even much nicer proof that using the amenable radical. But okay, I wanted to present the proof. Okay, so let me focus here. So here I had like several lemma. I look at the Levy decomposition, and then the first lemma is that if I consider a invariant probability measure on discrete subgroup of Q, then it must be inside L in the Levy part. Now, since the Levy part is not well defined, there are many of them, and the intersection of all of them is trivial, you deduce that if you have a p-invariant measure on discrete subgroup of Q, then it must be on the trivial group. And this is general and abstract, and before you use Neveu-Zimmer, this is just elementary stuff about parabolic subgroup. And now,
And how did you use this? So I lost. Where did
yeah,
you use?
So let's without looking at the notes say, so if you have now, suppose you have a stationary measure supported on discrete group, and suppose that it's not invariant. By Neveu-Zimmer, you have a parabolic factor. You have a factor which is G mod Q. This will imply this factor send a stabilizer into the stabilizer. Right, when you have factor map, the stabilizer in the origin space is contained in the stabilizer in the image space. So in the image space, which is G mod Q, the stabilizer are conjugates of Q. So in the original space, the stabilizer will be subgroup of conjugates of Q. So you get things which are, you get measures that supported, I mean, this disintegration of the measure, this disintegration of the, you have here the measure, here you have the measure nu Q, and here you have the measure, no, it's not, this is the Fürstenberg map. So here you have the measure mu infinity, and here it's project to nu Q. And the stabilizer of a point here is the conjugate of Q, and the stabilizer of a point here is some discrete group. But, okay, but the way that I learned to look at it from Uri is that if I do a disintegration of the measure here, then the measure, what sits above the Dirac measure of Q here, what sits here when you is the what sits above Q. If you do this integration of measure, you will get some measure on discrete subgroup of Q, which is invariant under the amenable radical of Q, which, and this will be enough. But okay, here I said it a bit differently. Did I answer your question or just confuse you more? Okay.
You once said some implications on the existence of unbounded harmonic functions, and also about some spectral gaps. Can you say something about that?
Not yet. Yeah, not yet. I think Margulis can say something about it. But yeah.
Something about what? What's the question?
There is a conjecture of Yao that I think Margulis knows how to answer based on this.
So what is the conjecture? What is the question?
The conjecture is that if you have a Riemannian manifold with infinite volume and positive Chigger constant, then it is not Liouville. That's a conjecture of Yau, which is false, and it's false due to Itai Benyamini and some co-authors. So actually, Itai's PhD was to construct an example that this conjecture in three-dimensional example, so just a metric on Rn. So I think so such that the conjecture is false. But for locally symmetric manifold, it could still be true. And what I learned from Margulis is that it follows, I think, from this. So, but yeah, don't ask me. This you should ask Margulis. But I hope to, yeah, somehow. Next month I give a talk in Yale, a Zoom talk in Yale, and maybe after that I will know more, if not before. But yeah, I don't see the implication. Yeah. More questions? Or?
Yes, I have a question about quantitative aspects. Is there any chance that you can prove something quantitative, generalizing your result? Like you know that you need to go at such distance before finding an injectivity radius of this side.
No, I don't think I can do that. So I see why you asked it. It seems like we have all the ingredients to do that. But yeah, maybe it's possible, but I don't see it at the moment. So you see, the thing is that in this work with Margulis and Aryeh, we get very good and very precise control, but only near the identity. And somehow we lose it when we go far from the identity. But it doesn't mean that it's impossible. It doesn't mean that, because maybe if you consider different approach, then maybe. So I have to think about it. So it doesn't follow from the existing literature, but if we modify somehow the metric that we use here, okay, I need to think about it.
So my motivation for this question is that, so as you said, your result is a generalization of the normal subgroup theorem.
Yeah.
And so there is this conjecture of Margulis and Zimmer about commensurated subgroups.
Yeah. Yeah.
So I was thinking that maybe it would be helpful to have some quantitative version.
Mm-hmm. Yeah. So, okay, my answer is I don't know. The second answer is I think there is a way to get a quantitative. I would guess that there is a way to get a quantitative statement. And my third guess is that it will not be enough for the Zimmer Margulis.
Yeah, it shouldn't be enough, but maybe it could be helpful. I don't know.
Yeah. But that's only guesses. But yeah.
Okay.
Thank you.
A related question. I think I know that I asked you, so I think I know that you don't know, Tsachik, but I want to mention a related question by Margulis is about ergodicity for the action on G mod P.
Yeah, that's equivalent to what Raz asked. So in fact, this is something that I can actually explain why ergodicity of lambda on G mod P is equivalent to a non-Liouville property for the manifold. Yeah, the equivalence between these two I see.
Sorry. So you say that Margulis is going to prove this using your...
So I think, okay, maybe it's better to stop the recording because now I'm speculating.